I want you to imagine that these skyscrapers behind me represent mathematics, with each building representing a different field, with this one being number theory, this one being analysis, and so on. Each floor represents a different concept in that field, with them being built on the floors beneath them, and new floors being constantly built every day. Now, this isn't a perfect analogy by any means, because in reality, all the buildings would be complexly intertwined, with bridges connecting each of the buildings, and each of the floors will be different sizes. But this perfectly captures the idea that I want to explore in this video, because after roughly 45,000 years of developing mathematics, about 300 years ago, several mathematicians started asking questions that would lead to a focus on rigour in mathematics. And in our analogy, those questions started with, where are the foundations of our buildings, and where is the ground? Mathematicians have been building up their fields to incredible heights, proving countless new theorems and identities that have helped shape the world in countless ways. But it's not till recently that some of the most fundamental ideas of these fields have actually been proven. For example, if I were to ask you to prove that 1 + 1 = 2, the first thing you'd do isn't to construct a proof for it, you'd probably ask, why is this question important? It's silly, and for good reason. Because why is it important to prove some of these obvious statements? Luckily, this example is in fact true, but there's been quite a number of times in mathematics where seemingly obvious statements have been assumed to be true, but later been disproven, and this has had some major consequences. For example, when Newton and Leibniz were creating the idea of the derivative, they made a crucial oversight that meant a whole rework of the idea was required, with the introduction of the epsilon delta definition of a limit. And this is exactly why rigour is so important. Now, admittedly, it is easier to prove that x + y = y + x, or that 1 + 1 = 2, than it is to prove the idea of a derivative. But some seemingly obvious statements can actually turn out to be false when we move into different areas of mathematics or consider a different set of values. But even if that's not enough of a reason to convince you that rigour is important, I think at the very least, there's a certain element of beauty or satisfaction that we can get from proving these identities and knowing that they're true. And it's something that can bring a lot of people real satisfaction and enjoyment. So in this video, I want to take you on a journey that goes through the creation of the natural numbers, the integers, and the rational numbers, along with all the operations that go with them, in an attempt to show you what advanced mathematics looks like, with the comfort and familiarity of the natural numbers we've all grown up with. Think of it as the training that you'd need to study mathematics at an advanced level, whether that be at high school, university, or even beyond. So to go about rebuilding mathematics with rigour, we have to assume absolutely nothing, because otherwise we could very easily end up with circular statements or paradoxes, which we don't want. So the first question we'll ask ourselves is, how do we build the most fundamental part of mathematics, the natural numbers? In 1889, Giuseppe Peano developed the 5 Peano axioms, which are 5 unprovable statements which we assume to be true, and when put together, they create the natural numbers. And we're going to go through each one and understand what they actually mean. N++ simply means the successor of n, which is notation we've borrowed from the coding language C. For our purposes, we'll just say that n++ means the next number along, where 0++ = 1, 1++ = 2, and so on. But it's important to note that n++ is actually a mystery function, because we can't define it using addition, since we don't have that yet. This means that rather than having 1, 2, 3, we could have 7, 5, 12, 6, 5, 9, or any combination of numbers. The only restriction is that the successor operation has to follow the 5 axioms, which we'll go on to look at now. The first and second axioms are quite simple. The first says that 0 is a natural number, and the second says that if n is a natural number, then the successor of n is also a natural number. In our context, what this means is that we can input 0 into axiom 2, and that gives us that 1 is also a natural number. We can then repeat this by putting 1 into axiom 2 again, and then getting that 2 is also a natural number. We can then repeat this process again and again infinitely, which gives us that every number greater than or equal to 0 is a natural number. It may not be as clear as to why the third and fourth axioms are necessary, but it's actually possible for us to end up in cycles where we have the successor of 0 is 1, the successor of 1 is 2, and then 3, but then after 3 we're back at 0. Now this would mean that the only natural numbers we have are 0, 1, 2, and 3, and we never actually define the rest of the natural numbers. But this problem doesn't just happen with 0, it can happen with any number, such as this example here. This is what the fourth axiom is for, as it stops any of these examples from happening, as it means that 3 and 0 can't both have a successor of 1. The final piano axiom is called the principle of induction, and besides from being useful, it's actually necessary to finish the construction of the natural numbers. Now let's say we had a set of two sequences of numbers which are completely separate from each other. Now this doesn't defy a single axiom at all, but it doesn't quite line up with the idea of the natural numbers that we're trying to obtain. Now the fifth axiom stops this set from existing, because it implies that it's not possible for P of n to be true for all n. Now it doesn't matter what property P of n actually is, since it's not possible to prove that any of the elements of B are actually true from 0. Now we've finally done it, and defined the set of natural numbers. Now this is all good and well, but there's absolutely no order to them at all. Like we said before, S of n doesn't have to output the next number along, and there's no notion of 1, 2, 3 yet. And whilst the set we've made contains all the natural numbers, there's nothing saying that one of them has to be bigger than another. Before we go any further though, I want to highlight how we define the natural numbers axiomatically, rather than constructively or practically. And what I mean by this is that we've not actually defined what the natural numbers are, only the properties that they have. I want to encourage you to treat maths this way, because it doesn't matter whether the natural numbers are represented by counting on your fingers, or Roman numerals, or any other abstract concept. All that matters in mathematics and to mathematicians is that a system follows laws and obeys logic and reason. Now this isn't the only way to construct the natural numbers, as using set theory and cardinality, we can come up with just as concrete of a system. And in some situations, this definition may be more useful, but in our context, neither is better than the other, because they both hold up against the test of logic and their axioms. The first thing we'll do is make sure that we can say that the successor of 0 is 1, the successor of 1 is 2, and so on. This will make it easier to define addition, as we're building upon what the successor operation actually is. It's important to note as well that this is a definition and not an axiom, with the difference being that an axiom is an assumption that we take to be true without proof, but a definition just provides meaning to a term or concept. The most reasonable next step to take forward is to define addition. We'll use this later when we come up with the idea of greater than and less than. Now all we've done here is define addition for 0. To be able to define addition for all the natural numbers, we'll have to use the principle of induction, which we came across earlier. This is actually a slightly altered version of induction, but I'll explain this after we've gone through the idea. We start by defining the base case, and then we assume that we've defined addition for the natural numbers. And we do this for the same reasons as before. If we can show that when it's true for a natural number n, then it's true for the next natural number, we can prove it for all the natural numbers by using the case n equals 0. And that's exactly what we do here. We define induction for n++, and then we use the identities of 0 plus m and n++ to prove things such as 1 plus m. Again, we actually mean the successor of 0 plus m, but for our case we're just using the idea that the successor of 0 equals 1. If we wanted to carry on and try and find what 2 plus m is, we could use the statements that we've already proven to help us find out what this is. As we can see, this is clearly n plus 2. What we've just used is a technique called a recursive definition, and while similar to induction, it's an idea which Richard Dedekind came up with before piano developed his axioms, and his work was actually so influential to the axioms that they're sometimes referred to as the Piano-Dedekind axioms. We'll use the concept a few times in this video, so it's good to know who we have to credit. It's also important to run through identities such as commutativity, associativity, and cancellation. But I won't go through the proofs of these for the sake of time. We now start forming the concept of order by defining what greater than means. We start by saying that n is greater than or equal to m if and only if n equals m plus a. When we say if and only if, what we mean is that both statements imply each other. In our example, we would say n is greater than or equal to m implies that n equals m plus a, and n equals m plus a implies n is greater than or equal to m. Furthering on this, we can also say that n is greater than m if and only if n is greater than or equal to m, and also n does not equal m. And the reverse is also true. There's a handful of ideas which we need to go through in order to prove order, and the first of those is called reflexivity, and it states that a is greater than or equal to a for all a that are natural numbers. We go about proving it by using induction. We start by writing out the base case. Now, obviously, 0 is greater than or equal to 0, since 0 is equal to 0, so this is obviously true. The next part of the proof is to assume it's true for some natural number a. We'll rewrite this as a equals a plus b, and we'll see why this is a good idea in the next part of the proof. The final step in this proof is to try and show that the statement is true for the successor of a. We'll start off by rewriting the statement using the definition of greater than or equal to, which we just created. Now hopefully the right-hand side of this equation looks familiar, because we can actually also rewrite this using the definition of addition that we came up with not too long ago. Now this is where rewriting that assumption comes in handy, because we can just substitute a equals a plus b into this new expression we have, and that gives us that the successor of a equals the successor of a, and that proves the statement. Now there are some other identities which we need to prove in order to finish our construction of greater than or equal to, but for the sake of time we won't go through these proofs and we'll just assume them to be true. With everything that we've just proven, we can now show that any two numbers fall into one of the three categories and divide the natural numbers into three sections. This will give the natural numbers order without us needing to do anything else. We start by showing that we can't have more than one of these statements true at any one time. If we had a is greater than b, then a wouldn't be equal to b, which is proved by the definition we came up with earlier. The same goes in the other direction. If we had b is greater than a, then a would also not be equal to b. If we had a is greater than b and b is greater than a, then again we rewrite them using the definition we came up with earlier. And then by using the anti-symmetry identity that we proved earlier, we can come up with the contradiction that a equals b when a doesn't equal b. This covers all possible groupings of two statements, so this proves that we can't have more than one of the statements true at any one time. The next part of the proof is that we have to show that at least one of these statements is true. We do this by inducting on a, meaning that we keep b fixed and we only worry about the base case and the inductive step for a. Looking at the base case, we can immediately notice that we can't have 0 is greater than b, since we haven't defined negative numbers yet. Regardless, we've proven that at least one of the statements has to be true, as we're left with b is greater than or equal to 0. Now, we assume the statement is true for some natural number a, and then we try and prove it for the successor of a. We'll go through each case, starting with a is greater than b. We can rewrite this as the successor of a is greater than or equal to b, using one of the properties of order that we came up with earlier. We can just rewrite this as two different statements. The successor of a is greater than b, or the successor of a is equal to b. Now whilst this does show that at least one of the statements hold for this case, I'd like to show you why we can't have the successor of a being equal to b. We do this by taking the obvious statement that the successor of a is greater than a, and then also the assumption that a is greater than b. And then using the property of transitivity, we can say that the successor of a is greater than b. And then by definition, this means that the successor of a cannot equal b. So that proves this case. For the next case, we have a equals b, which implies that the successor of a is greater than b. But why is this? Well, if we had a equals b, then it's obvious that the successor of a equals the successor of b. Since we've proven addition, we can say that the successor of a equals b plus 1. We can actually use the definition of greater than again here, as we can line up our terms with those of a equals b plus c, and it's obvious that the successor of a doesn't equal b, and so that means that we must have that the successor of a is greater than b, which proves the statement. Now for the last case, we have b is greater than a. Now we'll start by rewriting this as b is greater than or equal to the successor of a, using one of the properties of order that we came up with before. Similar to the first case, this shows that we must have at least one of the cases to be true. However, this time, we can have that b equals the successor of a. So whether b is equal to or greater than the successor of a, this case is true. So now, after proving all three instances of the successor of a, we've proven that at least one of these three statements must be true at a given time.
Now that we've provided order, we've finished in creating the natural numbers that we're all familiar with from scratch. Now, that was a lot of proof and heavy maths notation, but I hope it was reasonably clear. And don't worry if you have to re-watch this a few times to fully understand what we've just went through, because that was effectively a whistle-stop tour of the first sections of an analysis course you get taught at uni. In fact, everything we've been through so far is exactly how Terence Tao presented it in his book, Analysis 1, which he formed from when he taught the course himself. Now, if you've enjoyed or remotely understood anything that we've been through so far, then it'd probably surprise you to learn that we've been doing the exact same thing that an American uni student would do.
We'll go on to create multiplication in a bit, but before we do that, I want to make the set of positive numbers, as they'll be vital later on for other proofs. Now that we have the natural numbers, creating the positive numbers is relatively easy. We can simply say that a natural number is positive if and only if it isn't equal to 0. So we can create the set of positive numbers by just removing 0 from the natural numbers. A proof I'd like to run through is that a positive number added to any natural number is a positive number, and we'll use induction again to prove this. We start with the base case and consider a plus 0. Now this is obviously a, which we proved when doing addition, and since a is a positive number, the base case is true. Now we assume the statement to be true for some natural number b, and look towards proving the statement for the successor of b. We use the idea of addition again to get this statement. Now, by the second Peano axiom, no number can have a successor of 0, which means that a plus b cannot equal 0, and that means that a plus b will always be positive. Now that we've done all three parts of the induction, we can say that the statement is true for all positive numbers a and all natural numbers b. Now we move on to defining multiplication and later on exponentiation, which should both be reasonably easy to come up with, since exponentiation is just repeated multiplication, and multiplication is just repeated addition. We use a recursive definition again to come up with multiplication, by defining multiplication for 0, assuming we have done for some natural numbers n and m, then defining it for the successor. Next, we also prove identities such as associativity, commutativity, and distributivity. This last one is something we haven't encountered before, however, and we'll prove it now. We'll start by inducting on C, and we'll keep A and B fixed. So let's start with the base case. The left-hand side simplifies down to AB, and A times 0 we define to be 0. So we have AB equals AB, and so the base case is true. We then assume the property to be true for natural numbers A and B, and then we prove it for the successor of C. Firstly, we'll rewrite the successor of C as C plus 1, and we can then use the assumption we had to rewrite this as AC plus A. We rewrite the addition on the left-hand side, and here is where we make the crucial jump. Using our definition of multiplication, we can see that if we take m to be a and n to be b plus c, we're able to rewrite the left-hand side to a multiplied by b plus c plus a. Finally, we use our assumption one last time to simplify the left-hand side to ab plus ac plus a. Now that we've proven distributivity for c equals 0 and the successor of c, and assumed it to be true for c, we can say that the law of distributivity is true for all a, b and c that are natural numbers. Around 300 BC, Euclid wrote his books titled The Elements. These were and still are fundamental texts for logic, number theory, and a large part of mathematics. In the seventh of his 13 books, one proposition he theorized was that any natural number n can be divided by a positive number q to obtain a quotient m and a remainder r, where r is less than q. We're able to prove this statement now with what we've already proven, and once again we'll use induction to do so. So, by inducting on n and keeping the other terms fixed, we have 0 equals mq plus r. But how do we show that there are natural numbers m and r that satisfy this equation? We can't subtract r from both sides because we don't have subtraction yet. What we need to do is turn this into a slightly simpler problem which is clearer on how we would solve it. Now this simpler problem is showing that if a plus b equals 0 and a and b are natural numbers, then a and b must both be 0. To prove this, we'll use a technique called proof by contradiction. How this works is that we assume the opposite of what we want to prove to be true. In our case, this means that we say a isn't equal to 0. Now, this would imply that a is a positive number, which by our previous definition of a positive number would mean that a plus b is also positive. But we just said that a plus b equals 0. So by substitution, this would imply that 0 is a positive number, which is false. And that means that our original assumption must have been false. so it actually turns out that a does equal 0. We'd reach the same outcome from the same process if we assumed that b didn't equal 0 as well, so we don't need to worry about that. With the statement proven, we now have to look at what this means for the division lemma. Well, if mq equals a and r equals b, then we must have that mq equals 0 and r equals 0. We found r now, but what about mq? Well, either m or q must be 0, and we defined q to be positive before, so that means m must be equal to 0. And with that, we successfully found natural numbers m and r that satisfy the base case, so it's true. Now we assume that the statement is true and try to prove it for the successor of n. We start by simply applying the successor operation to both sides of the assumption. We simplify this out, giving the successor to r. Now, we turn to the conditions of the lemma, which will be more useful to us now. They state that r is less than q, but is greater than or equal to 0. In our circumstances, however, we have the successor of r and not r, and using one of the laws of order, we can change this to q is greater than or equal to r, but greater than 0. Technically, we haven't proven that changing r to the successor of r must mean that r is greater than 0, rather than greater than or equal to. But the proof is just a case of applying the successor operation to both sides, then using the same proposition. And since it's not even vital to this proof, there's no need to explicitly run through it. Now though, we have that q is greater than or equal to the successor of r. The left statement implies the same proposition we started with, since nothing in the conditions changed except the greater than 0. If we have the successor of r equal to q, however, we can rewrite the statement as n equals mq plus q. Using distributivity, we have that n equals q times by n plus 1 plus 0. Now this proves the statement, since we'd have q being m plus 1 being q, and r being 0. With this, we've proven the case of the successor, and we've proven that the division lemma is true. Now we move on to creating the integers and the rational numbers. The integers need negative numbers, and they require subtraction to be formed. But subtraction requires negative numbers to be formed themselves. So we have a sort of chicken and the egg problem here. The way we get around this is by using different notation, and this is the way we define an integer, where a and b are natural numbers. We'll still refer to this as a minus for convenience, but just bear in mind that this is merely a placeholder. We say two integers are equal if and only if a plus d equals c plus b. We go about the same process of defining multiplication and addition for the integers, but this time we don't need recursive definitions, since we're just extending the domain of the operations, rather than recreating them entirely. Notice how these operations work in the same way as they do with the natural numbers, and this means we can say there is an isomorphism between the natural numbers n and the integers that take the form n minus 0. For those who don't know already, the three lines here mean identical to. After we've defined these two operations, we're free to prove all kinds of things for the integers and finish our construction. We can define the negatives of the integers, where if a minus b is an integer, then minus a minus b is b minus a, which actually soon follows on to us being able to define subtraction properly. We can also divide the integers into three parts again in a similar way we did before, but with some different ideas involved. We'll give the integers order later on when we prove the lower statement. We can collect our laws of addition and multiplication, along with a couple of others, into these statements, which are simply the basic laws of algebra. Together, these properties make the integers a commutative ring. Now, I could go on and talk about how this means we have an abelian group closed under addition and multiplication, and it has associativity, but realistically, this is nothing more than a flashy name from group theory, saying that the integers have these said properties. Now don't get me wrong, group theory is a highly interesting subject, but we don't want to go off on too much of a tangent, so it's something you can look into if you're interested. We'd have to prove all of these identities again for the integers, since in theory, we don't have any way of knowing whether they work. We prove them to be true for natural numbers, but the integers are a larger set because they have a larger domain. So it's not possible to say identities for the natural numbers are true for the integers. However, we can do the reverse. We're now able to formally define subtraction using the concept of negation, so we can get rid of that placeholder notation now. But before we do, Let's make sure that these are actually the same operation. If we say a minus b is a plus minus b from this definition, then we can actually express this using our original definition of what an integer is. And this simplifies down to the same statement, but using the placeholder notation, which is good news. Now we go about proving the same properties of order we did for the integers, but this time for the rationals. There's two new properties I want to take a look at here though. The first says that a is greater than b if and only if a minus b is a positive integer. To prove this, we split it into two cases. One where the left implies the right, and the other where the right implies the left. We'll start with the statement on the left. To prove this, we have to work from a is greater than b to a minus b being positive. We'll start by saying that a equals b plus c from our definition of greater than. Now rather than using the condition a mustn't equal b, we can just say c must be a positive number, since it can't equal 0. Thanks to subtraction, we can rearrange this into a minus b equals c. Now this is saying a minus b must be a positive number c, so this proves the statement for this case. For the next case, we don't have to put in any extra effort at all, as we can just do what we've just done, but in reverse. Now that we've proven both the forward direction and the backwards direction, this means that the whole statement must be true. The next statement says that a is greater than b implies minus a is less than minus b, or in other words, that negation reverses order. We go about the same process by starting with a is greater than b, then working towards minus a is less than minus b. We start by saying that a minus b is greater than 0. Next, using the idea that addition preserves order, we can add the negation of a to both sides. After simplifying, that leaves us with minus b is greater than minus a, which proves the statement. Now we move on to creating the rationals, and bring division into our arsenal of operations. We define the integers to be the difference between two numbers, and we'll define the rationals in a similar way, by saying that a rational is any number that takes the form a over b. Again, to steer away from the chicken and egg problem and circularity, we'll use placeholder notation rather than using the vinculum notation. Crucially, we say that any rational cannot have b equals 0, as that is undefined. Not infinity, but undefined. In the same way we came up with how two integers are equal, we'll say two rationals are equal if AD equals CB. As always, we define addition, multiplication, and this time the new operation of negation for the rationals. We have the same laws of algebra which we'd have to prove again, since the rationals are an even larger set than the integers, an idea we'll come back to towards the end of the video. There's a caveat here, however, as there's a new identity which we need to add, the inverse. We say that the inverse of a rational a over b is defined as b over a, where a and b aren't 0, so we don't have division by 0. Introducing negation makes it vital to add the identity x multiplied by its inverse equals 1, as this completes the definition, and also allows us to call the rationals a field, which is sort of an upgrade from the commutative ring of the integers. Now, we're also able to throw away the old placeholder notation and use the good old vinculum. Finally, we also define subtraction for the rationals, and positive numbers for the rationals as well. After this, we can order them, and call them an ordered field. We move into some slightly less familiar notation here by defining absolute value using a piecewise function, which effectively just says that the absolute value of x is simply itself when x is greater than 0, 0 when x is 0, and it outputs its negation when less than 0. All this operation does is tell us the distance of a number from 0 on the number line. The absolute value of 4 is just 4, and the absolute value of minus 5 is simply 5. If we carry on with this idea, we get the concept of distance, which is just the absolute value of x minus y. This means the distance between two numbers, rather than the distance from 0. For example, the distance between minus 5 and 3 is 8. There's identities for both absolute value and distance, which are both pretty similar. We'll take a look at 3 that we aren't very familiar with and are quite interesting. The first is part of a property called non-degeneracy, and says that the absolute value of x is 0 if and only if x equals 0. As we've done before, we split this into two statements, one implying that and one being implied by. We start with the implies. If we had x is greater or less than 0, then we'd have that the absolute value of x is greater than 0. And since we've shown that any one of these three cases is true, the only case where this is possible is when x equals 0. For the implied by statement, it's simply true by definition. The next statement is called the triangle inequality, and its name derives from the idea that in a triangle, such as this one we've constructed using vectors, the length of one edge is always less than the length of the other two edges combined. Now, this isn't formally what we're trying to prove, but it's the core idea behind the identity. To prove this, we have to consider each combination of cases. If we start with both x and y being greater than or equal to 0, we must have that x plus y is less than or equal to x plus y, and since these are equal, this case is true. For the case x is greater than or equal to 0, but y is less than or equal to 0, the right-hand side must be equal to x minus y, but for the left-hand side, it depends on whether x plus y is greater or less than 0. If we have x plus y is greater than 0, then we have x plus y, which overall simplifies down to minus y is greater than or equal to y. But since y is a negative number, or 0, then this is true. If we had x plus y is less than 0, however, this would mean we're taking the absolute value of a negative. So we take the negation of x plus y, which overall gives us minus x minus y is less than or equal to x minus y, which simplifies down to x is greater than or equal to minus x. And since x is positive, this case is true. We'd reach the same conclusion if we had the opposite statements instead. So both of these two cases are true. For the final case, if we had x and y are both less than or equal to 0, then we'd have minus x minus y is less than or equal to minus x minus y, which are equal, so this last case is true. This proves the whole idea, and we are done. The final identity states that we have y is greater than or equal to x, and x is greater than or equal to minus y, if and only if y is greater than or equal to the absolute value of x. To prove the implies side, we split the statement into two. Y is greater than or equal to x, and after multiplying by minus 1, y is greater than minus x. Now it doesn't matter whether x is positive or negative, because y will always be greater than x. And because of this, we can actually say that y will always be greater than the absolute value of x. And so this case is proven. For the implied by case, we start with the obvious idea that the absolute value of x is greater than 0, and therefore y is greater than 0. Since y is greater than 0, this must mean that y is also greater than minus y. And because the absolute value of x is always greater than x and minus x, it doesn't matter whether x is positive or negative. So we can simply now say that y is greater than or equal to x, and x is greater than or equal to minus y, proving the statement. The last operation we'll define is exponentiation, and we'll use a recursive definition since we haven't formally used this before. Now, just like the other operations, there are some properties we need to prove, and they aren't too different from the ones we've already seen. So, in fact, I challenge you to have a go at trying these proofs. I'll leave some hints in the description if you decide to have a go. But now, I want to return to the rationals to explore one final idea. What I want to look at is the idea that there are no rational numbers which can satisfy the expression x squared equals 2. This is a very famous proof, which we credit to Hippasus of Metapontum, a member of the Pythagorean cult, who was supposedly sentenced to death by the Pythagoreans because of this. So it's quite easy to say that this is an interesting statement. To prove this, we assume x squared can equal 2 for the sake of contradiction. We can rewrite x as a over b using the definition of a rational, and then we can multiply through by b squared to obtain a squared equals 2b squared. But what now? Well, we have to take a step to the side, as we need the idea of even and odd numbers to continue. We'll define an even number to be a natural number p that can be written as a product of some other natural number k multiplied by 2. An odd number is the same, but we also add 1. We need to show that a number has to be either even or odd, And the first thing we'll do is show that a number can't be both even and odd at the same time. Let's say a number can be, for the sake of contradiction. This would imply from our definition that 2k equals 2k plus 1, which simplifies down to 0 equals 1, which is false, so we can't have a number which is both even and odd. To show that a number must be either even or odd at all, we have to use Euclid's division lemma again. If we simply set q equal to 2, then this is enough to show that every number is either even or odd, since for any natural number n, we can find a natural number m and r that satisfy the statement. The next statement we have to prove is that if a is odd, then a squared is also odd. By doing this, we also end up creating our first quadratic. So we expand 2k plus 1 squared, and we end up with 4k squared plus 4k plus 1, which we can factor 2 out of to end up with 2 times by 2k squared plus 2k plus 1. And since this is some integer multiplied by 2 added to 1, then this is an odd number. With these three statements together, we're now able to continue on with our proof. So, what do we do now from a squared equals 2b squared? Well, we know that a squared must be even now from our definition, and since there's no odd number which gives an even number when squared, and also that every number must be even or odd, then we must have that a must also be even. So we'll rewrite it as a equals 2c. Substituting this back in gives us 4c squared equals 2b squared, which simplifies down to 2c squared equals b squared, which by the same methods give us that b squared is even and b is even. Now we can carry on doing this and we end up with an infinite chain of statements just like this. Rewriting this using the other definition of the variables, it's clear to see that we have a sequence of variables which are all decreasing. Since if a equals 2b, then a must be greater than b, and b must be greater than c, and so on. Now this step is vital, so we'll once again run through yet another obvious proof. If we suppose the opposite to be true, and that b was greater than or equal to a, then by a equals 2b, we'd have b is greater than 2b, and that 1 is greater than 2. So this can't be true, and we must have that a is greater than b, where a and b cannot equal 0, and therefore none of the variables can. Now, what we've identified is that we have an infinitely decreasing sequence of natural numbers which can never equal 0. But this is exactly the problem. This can never happen. No matter what sequence of natural numbers we have, if they're always decreasing, they'll always end up at 0, or in our case, 1. But it's not good enough to just claim that this is true. We also need to prove it. So we have that every nth term must be greater than the n plus 1th term, and that every term must be greater than 0. Now, this is the base case we'll use for an induction on k. We assume that all terms are greater than this value k, and then for the sake of contradiction, we assume that k plus 1 is greater than ai for some I that's a natural number. Next, we can clearly say that k plus 1 is greater than k. Subtracting k here gives us that 0 is less than am minus k, which is less than 1. And by applying the successor function to everything here, we have that 0 is less than am minus k plus 1, which is less than or equal to 1. And we can simplify this. This gives us that am is less than k for all m greater than I, and this contradicts the inductive hypothesis, which proves the whole statement, and says that we cannot have a sequence of natural numbers in infinite descent, and therefore there is no rational number that satisfies x squared equals 2. There's nothing special about 2 though, as we could also prove the same for 3, or any non-square number. And this clearly shows that the rational numbers have gaps. The last idea I want to look at is that between any two rational numbers, there is always at least one more to be found. To prove this, we start by defining z to be the average of x and y, which we know will always be rational. Next, we simply use the fact that y is greater than x. We then divide both sides by 2, and then add y over 2 to both sides. This gives us that y is greater than x plus y over 2, which is actually just our definition for z. So y is greater than z. If instead of adding y over 2, we were to add x over 2, we would get that z is greater than x. Now the reason these two identities are so interesting is because it means that unlike the natural numbers, you can't zoom in on the number line as far as you want, but in the rational numbers, you can. since there's always a new rational between any two other rationals, and we could say that the rationals are infinitely dense. However, we said there were also gaps in the rationals because we said that x squared cannot equal 2. So what does this mean? Well, the only way to put it is that the rationals are both infinitely dense and have an infinite number of holes as well.
You can't deny that this isn't true, because I've just walked you through the proof that says that this is how the rational numbers are. But now, we've proven that the ground is actually there, and that the foundations our buildings are built upon are steady. And I hope you can admire how much there is to appreciate of the buildings when we're looking up from down below. None of these statements, and in fact none of mathematics at all, would have been possible without proof. And everything that we've just proven is only just looking at the beginning, because after this we could go on to prove everything to do with the real numbers and construct them, and then move on into calculus and look at ideas of limits, sequences, derivatives and integrals. But even then, we're still only looking at the tip of the iceberg, because several parts of number theory and all the different fields of analysis also require proof, and frankly all of maths does, all of pure maths. But that is obvious because it's one of the biggest concepts in maths. If these buildings behind me represent all the different fields we have, then the proof is the cement that holds it all together. Creating the natural numbers that we know today, not today, I think it was